In this video, we are going to be going through lecture number 3, that is the unit conversion and dimensional analysis concepts. So let's have a look. Now, before we get into this, one kind of final note cap on the precision and accuracy discussion that we had at the end of lecture number 2, and that is, how do we actually show precision and accuracy? And the answer to that comes from your textbook, section 1.7. As you know, precision is the measurement of agreement between values, measured values, and accuracy is a measure of how close those measured values are to the true value of the substance that you're measuring. Now, in terms of ways of measuring precision and accuracy, there are two tendencies that we tend to fall upon. There is what is called the standard deviation. And the standard deviation is a measurement of how far apart an individual data point is from the overall average of all of the measurements of that particular substance. And so if I look at the standard deviation for this one point, and I kind of bring it together with all the standard deviations for all the other points that are measuring that same item, I get an idea of how close those items are to each other. The more variance, the more variability there is in the data, the larger that standard deviation is going to be. Whereas the closer those data are to each other, the less variance there is, the smaller that standard deviation is going to be, and the better we would say that the precision is as a result. Now, another way of looking at these two is something called a confidence interval. Confidence interval tells us the probability that a measured value or a range of values actually contains the true value. So usually we measure a confidence interval. We take the mean, the average of all of our measurements for that particular data, and we attach to it error bars. And depending upon what our standard deviation is, depending upon the spread of our data, we put on those error bars and we say, okay, with error bars this big, we are going to give a 95% confidence that the actual value is between these two values here. And maybe with 99% confidence, we can spread them out a little bit more. 99.9% confidence, we can spread it a little bit more. So generally speaking, what we see with a confidence interval is it's going to have a percentage value attached to it. A 90% confidence interval, a 95% confidence interval. And what that percentage tells you is this is how likely that the true value is within the range of those two error bars. So just a little bit to kind of put to a close the idea of accuracy and precision from a quantitative measurement standpoint. But now we're going to move into taking those units that we looked at the beginning of lecture number 2 and bringing them about a way for manipulating them from one unit system to another. And this can be within the customary system, this can be within the metric system, or this can allow us to bridge between the two systems as well. But all that we're doing in any unit conversion problem essentially is multiplying by 1. And we can say that because when we are using these conversion factors, these fractions, the value on the top of the fraction and the value on the bottom of the fraction are identical to each other. So we know by definition, 1 inch is equal to 2.54 centimeters. They are equivalent values to each other. So if I put them in a fractional form, since the value on the top is equal to the value on the bottom, that is essentially like multiplying by 1 because the values on the top and the bottom are the same, or at least equivalent to each other. And so I can interconvert between centimeters and inches using either one of these fractions, depending, and which one I use just depends upon what the circumstances are and what I need it for. Unit conversion is often described as being a function of dimensional analysis. Dimensional analysis is just a method, a process by which we are able to set up these conversions to help us to cancel out the units that we don't want and leave behind the units that we do. So we will see these in chapter 1 here as a way of doing conversions between units and unit systems. We'll see it in other places, chapter 2, chapter 7, chapter 8, and so on, where we will actually use it for things like converting atoms into molecules or converting one reactant into a product in stoichiometry. The same process is going to apply throughout here. But the idea behind it is relatively simple. I have a unit that I measured in. I have a unit that I want to convert it to, and I need to do some kind of calculation step to get me from one to the other. That calculation step that's involved is the actual unit conversion, the equivalency that we talked about in the previous slide. And the way that we set up that equivalency fraction is in such a way that the numerator containing the units that we want to get rid of is matched by the same unit in the denominator of the conversion factor. So that when we multiply the units together at the end, I'll have my initial unit multiplied by my desired unit divided by my initial unit. And since I have an initial unit in the top of the fraction and on the bottom of the fraction, they cancel out, and the desired unit is the only thing that is left over. So you can set up these kinds of conversions over a number of different scenarios, and they will always work toward the overall goal of keeping it organized, keeping your data and things kind of nice and orderly and straight, and probably most importantly, allowing you to do the conversions and have nothing left behind when you do. So this here I pulled out of another textbook. This is a common conversion factor table. So this will allow you to convert between the customary system and the international or metric system relatively easily. Remember, all of these things that are linked together by equal signs can be converted into fractional forms. So the 1 meter to 1.094 yards can be 1 meter over 1.094 yards, or it can be 1.094 yards over 1 meter. Which one do we use? Well, it depends on the circumstances. It depends on what we're trying to cancel out and where that unit is. If the unit is in the denominator, then we're going to want to make sure that in the conversion factor, that same unit is in the numerator so that they cancel out. If it's in the numerator, we want to make sure that the canceling unit is in the denominator, again, so they cancel out. Now, this table will be provided to you for all of your quizzes and all of your exams for anything that we do in this course. You are not responsible for having to know the conversions between any of these units and each other. However, the same cannot be said for the metric prefixes that we looked at in lecture number 2. Those metric prefixes, you are responsible for knowing and knowing how to convert between them. So do keep that in mind. But let's go ahead and do a couple of examples here on how to use this factor canceling method, dimensional analysis, to solve some interesting problems. So for example, the speed limit on Interstate 70 between Denver, Colorado and Kansas City, Missouri is 75 miles an hour for most of the distance. How many hours will it take to travel the 604.9 miles between the cities? And for the purposes of this exercise, we're going to ignore the fact that you will have to get out at some point and stop, or the fact that around certain areas the speed limit is going to change. We're just going to assume a flat average speed of 75 miles an hour and that you're able to go the whole way without going to the bathroom or stopping to eat or anything like that. Now, when you have problems like this, what you want to do is you want to identify what is the measurement that I am trying to convert. You may initially think that it's the 75 miles an hour. After all, that is a measurement of speed. However, the real measurement that we're going after here isn't that one, but rather the 604.9 miles that you will have to travel. So that's where we start. We start with the unit that we measured, the 604.9 miles. And what we want to do is we want to convert that into hours. This is where our 75 miles per hour come in. Now, 75 miles per hour means that you will go 75 miles in 1 hour, which means that 75 miles in this case is equal to 1 hour of time. Remember, anything that we can tie together with an equal sign can become a fraction in a conversion factor. So what we want to do is take that 604.9 miles, and using this as a conversion factor, I have miles in the numerator, so I want miles in the denominator of my conversion factor, which means hours is going to be the numerator. My numbers, 1 hour is equal to 75 miles. And so when I do this, my calculation, 604.9 multiplied by 1 divided by 75 to two significant figures gives me 8.1. My unit, I have miles multiplied by hours divided by miles. So my miles cancel out. Overall, this is an 8.1 hour trip. Now, from a significant figure standpoint, why did I stop at only 2? Well, the reason is this 75 miles per hour is a measured value, as well as the 604.9 miles. And so when I have multiple measured values that I'm multiplying together, weakest link principle applies. I only had 2 significant figures for the speed, so I'm only going to be able to have 2 significant figures for the time. 8.1 hours is the correct way to round it. Let's take a look at another problem. Fuel economy relates to the distance a car can travel on a set amount of fuel. If a car has a rating of 41.7 miles per gallon, what will this fuel rating be in kilometers per liter? And so again, here's that word per. Miles per gallon indicates that we've got a fraction, 41.7 miles is equal to 1 gallon of gasoline. Now, that is the only measured value that we have. So that's where we're going to have to start. And so we're actually going to start here with a fraction, 41.7 miles divided by 1 gallon. Now, in the end, we want to convert this into kilometers in the numerator and liters in the denominator, which means that I'm going to have to do 2 steps here, or at least 2 sets of calculations. I'm going to have to turn the miles into kilometers, so I need to have some kind of a conversion between those 2. And I need to turn the gallons into liters, so I need some kind of a conversion between those as well. Where do I go for that information? Well, this is where I want to go ahead and use that conversion table. And so I go to the conversion table here, and I see that for distance, one mile is equal to 1.609 kilometers. And for volume, gallons to liters, 1 gallon is equal to 3.785 liters. So I've got both of the pieces of information that I need. Now I just need to use them. And so I'm going to make a quick note for myself here. 1 mile is equal to 1.609 kilometers. 1 gallon is equal to 3.785 liters. Now that I have that information in front of me, now I can put it to good use. So starting with my 41.7 miles in 1 gallon, my first step is going to be to convert the miles into kilometers. Since I have miles in the numerator, I'm going to have miles in the denominator here and kilometers up top. The conversion is 1.609 kilometers for every mile. I can see I've got miles in the numerator and in the denominator, so they are going to cancel. The other conversion is gallons to liters. Here I have gallons in the denominator, so I want to put gallons in the numerator so that it cancels. Liters in the denominator. Conversion is 1 gallon for every 3.785 liters. My gallons in the numerator and the denominator cancel, and so all I am left with at the end are kilometers and liters, which is exactly what I wanted. So now we go back to adding, or rather multiplying all of this together. Multiply by all of the numbers in the top, divide by all the numbers in the bottom, so you can do it all in one calculation step. 41.7 multiplied by 1.609, multiplied by 1, divided by 1, divide by 1 again, and divide by 3.785. And we get to 3 significant figures, 3 sig figs this time, because the ones here are all exact. So I've got 3 sig figs, or excuse me, 4 sig figs in this conversion, 4 in this one. I only started with 3. Weakest link tells I'm going to need 3 then. 17.7 kilometers per liter is the resulting speed. All right, one more problem here. A 1960 silver quarter is found to have a mass of 6.25 grams. On a given day, the value of silver is $17.32 per ounce. How much is this coin worth if the coin is 92% silver? What I would invite you to do here is go ahead and pause the video and try to do this one on your own. I'll pause here just for a second to give you time to do that. And then hit play again when you're ready to check your answer. Okay, so there's a couple of pieces of information here that are useful to us. First of all, we have a measured value. The 6.25 grams is our measured value. That's where we're going to start, 6.25 grams. Now, where we go from here is kind of we've got multiple places that we have to look. So first of all, we need to turn this grams into ounces. So that will give us our ounces for this part where we talk about how much money it's worth. But before we can apply that conversion there, we're going to need to take into effect that this is a 92% purity coin. So all of the mass in that coin is not just silver. 92% of it is, the other 8% is not. So before we figure out how much money it's worth, we're going to have to apply that correction to the mass. And then once we have that correction taken care of, then we can convert it into dollars using the price of silver there. So everything that we have, we've been given in some kind of way. We know that $17.32 is equal to 1 ounce of silver. We know that 100 grams of coin are equal to 92 grams of silver. That's the 92% part. What we're missing is the relationship between ounces and grams. And so once again, we're going to have to go back to the conversion table. And in that conversion table, we're going to see that 1 ounce is the same as 28.35 grams. So now with that information in tow, we should be able to do everything that we need to do. So here's an example where once we start to get into things that are impure or that are chemical reactions, simply having a unit there may not be sufficient. Having a unit and also a descriptor of what that unit is describing is sometimes useful and helpful to us. And so to show you what I mean by that, let's take a look at this one. We have a 6.25 gram coin. So the descriptor I'm using there is the word coin to indicate that this is not an element or a compound. This is some kind of a mixture. And this is going to set us up as being kind of different. Now, using this second conversion factor, 100 grams of coin are equal to 92 grams of silver. So we are actually applying that 92% piece here. You can apply it really anywhere along the way. You just got to make sure that you apply it at some point. We can see that grams of coin are common, so they cancel out. Now that I have 92 grams of silver, I've converted 2 grams of silver. Let's go ahead and convert that into ounces. So grams of silver into ounces of silver. For every 28.35 grams, I get 1 ounce. So now we've done the conversion between grams and ounces. Last step, 1 ounce of silver is worth $17.32. My ounces of silver cancel out. I'm left just with dollars. 6.25 multiplied by 92, multiplied by 1, multiplied by 17.32, divided by 100, divided by 28.35, divided by 1. My calculator spits out 3.51287 and some other numbers that I know aren't important. From a sig fig standpoint, how many do I keep? Well, this measurement has 3 sig figs. This conversion has 4. The percentage only has 2. So from a technical standpoint, based upon that, $3.50 would be considered the most correct, at least according to our rules for significant figures. However, it would be easily acceptable to round to the cent, since that's our lowest form of currency. So $3.51 would be considered acceptable here as well. So that is it for this particular mini lecture. If you have questions, please feel free to bring those to our next lecture session on Zoom or in person, and or you can send me an email or a remind message as usual. But until then, have a good day, and I'll see you next time.